Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and get started calculating probabilities using the addition rule. So, depending upon the events that we're dealing with, right, we may or may not have overlapping sets. So let's consider the data in this table. Suppose that, right, we had a poll given to students, and we were asked about calculating the probability that a randomly selected student said a few are friendly or said none are friendly. And so let's go ahead and look at the data in our table. If we want to know the probability that a student said a few are friendly, we're going to go ahead and find those totals from our table. It looks like how many students said a few are friendly. Well, 3,735 students said a few are friendly out of my total 49,210 students. And so just the probability that a student said a few are friendly would be 3,735 out of my total number of respondents, 49,210. Or said none are friendly. So how many said none are friendly? Well, we've got to go find a different number. Now we're looking for none are friendly, so that's going to be 530 respondents said that none are friendly. So that would be 530, and that's still out of my total 49,210. Our addition rule, right, for the probability of events is just that. We sum together the individual probabilities of two events so long as they are mutually exclusive. So that's how we get the name for the addition rule, because we just add together the individual probabilities if we're dealing with mutually exclusive events. So what does it mean to be mutually exclusive? Well, it means that those events can't occur at the same time. It's like the shoe data from last class period that was shared with you. You can't be wearing shoes that are predominantly black and shoes that are predominantly white all at the same time. You got to pick one, right? And so here you had to pick one. You either said a few are friendly, or you said none are friendly, or you said all, most, or some, right? So you couldn't pick multiple rows there. You had to select one response. And so they're mutually exclusive. We can add the individual probabilities together. Now, I'm not sure what that is, so I'm going to go ahead and use my calculator to do that. We saw that we can calculate probabilities and write your answer as a fraction. We can write it as a decimal, or we can write it as a percent. And so for this, I'll go ahead and go right to a decimal and percent. I'll add together my numerators, since my denominators are the same. 3735 plus 530 out of my 49,210 respondents. So it looks to me like I'm getting about 8.7%. This means that if I were to randomly select one of those 49,210 students, right, if we were just to randomly select one of them, the chance that they either responded a few are friendly or none are friendly is 8.7% chance, right? Does that make sense? All right. So what happens if my events, right, are not mutually exclusive? We can refer to that as overlapping informally. And so consider the second problem. That is the probability that a student said none are friendly or they are a boy, right? How are these events not mutually exclusive? How are they overlapping? Well, we still can figure out how many students said none are friendly. We go and we find that, and it looks like the none are friendly is the same 530 as last time, right? The probability that said none are friendly is 530 out of my 49,210. Or they are a boy. Well, I can figure out the total number of boys there. It looks like there's 23,999 boys out of my total 49,210. If these were mutually exclusive, it would be the same as last time. We'd add the individual probabilities together. But what's different about this one? Well, don't we have some boys that said none are friendly, right? We've got overlapping data. This middle portion right here of my two different sets include boys who selected none are friendly. And so the people that said none are friendly, those boys are counted once when I do the probability of A. Then they're counted again when we do the probability they're a boy. And so we have to subtract off that overlap, that double count, right? So that we get the proper numerical value. Let's go ahead and see what that looks like. So here we go. Said none are friendly. There's my red 530 out of my total 49,210 plus probability they were a randomly selected student as a boy, right? How do we get that? Well, how many boys are there? There's 23,999 out of my 49,210. And then, because we've counted, right, we've counted those boys who said none are friendly once in the red 530. We've counted them again in the green 23,999 boys. So we need to subtract off that overlap. And that's the only difference between overlapping events versus, bless you, mutually exclusive events. We're going to subtract off those, namely, boys who said none are friendly. So where do we go to find that? Well, we need to find how many boys said none are friendly. So here we go. We'll go ahead and look, and we'll see right here. 480 boys said none are friendly. They were counted once in my said none are friendly, right? They're right there in that 530. They were counted again in the 23,999. They were counted again right there. So what do we need to do? We need to subtract off that overlap. They've been double counted, so we need to subtract off one count. What do you mean one count? We need to subtract off those boys who said none are friendly. That's 480 because they've been counted twice. This is still the addition rule. It's just the addition rule for overlapping events. That is not mutually exclusive. So the point of yesterday's activity, if two events are mutually exclusive, that means they can occur at the same time. And we calculate their probabilities simply by adding their individual probabilities together. If events are not mutually exclusive, that is overlapping, we still calculate the probability that A or B could occur by summing the individual probabilities. Then we just subtract off that overlap to avoid the double count. Let's finish this out with the calculator. So once again, I'll go ahead and do, since the denominator is all the same, I'll do 530 plus 23,999 minus those boys who said none are friendly. Did you notice that chart? 480 boys said none are versus only 50 girls said none are friendly. Those boys are unfriendly. Subtract off the overlap, close, divided by 49,210. I mean, I am. 49,210. And voila! Looks like 48.9%, about 48.9%. Awesome. What questions do you guys have about 1 and 2? So that was the key difference for mutually exclusive, right? They can't occur at the same time, events, versus not mutually exclusive, or overlapping events. Those events could occur at the same time. In other words, you could be a boy and select none are friendly at the same time, versus you couldn't pick a few are friendly and none are friendly at the same time. Those are mutually exclusive, right? It's like a freshman student and a sophomore student. You can't be both a freshman and a sophomore at the same time, right, when you complete your survey. However, you could be a sophomore student and an advanced algebra student at the same time because there are sophomore advanced algebra students. See, that would be a not mutually exclusive event because they could occur at the same time. But just because you're an advanced algebra student doesn't mean you're a sophomore. There are freshman advanced algebra students. There are junior advanced algebra students. There are senior advanced algebra students. And so those, right, in the situation are mutually exclusive versus not mutually exclusive in context. And we'll look more at that today. Awesome. All right. So let's go ahead and make sure that you're comfortable with your final exam. I'm going to go ahead and pause the recording while we talk about this because it'll be different rooms. There are going to be different rooms based on which class period you're in. We're going to go ahead and designate our classroom, right, for this hour, and then I'll resume the recording after this. Let's continue and make sure that we're comfortable applying the addition rule to calculate the probabilities of mutually exclusive versus overlapping events. Let's go ahead and consider this first scenario. This is made-up data for the shoes, different than you had last time. Let's suppose event A is you wore black shoes today. Let's suppose event B is you wore white shoes today. If you have to pick your predominant color, then there's no way you can be wearing predominantly black shoes and predominantly white shoes at the same time. Therefore, they're what we call mutually exclusive events. Everybody find this example in your note sheet. Let's calculate the probability based on this data. Their probability assume wore black or white shoes today. So what do? Well, it looks to me like our Venn diagram, picture is worth 1,000 words. These are mutually exclusive events. There's no overlap. And so to calculate their probabilities, we'll simply sum together their individual probabilities that event A or event B occurs. So let's go ahead and do that together. Event A, that is probability of student wore black. So we'll find that. Looks like black is 27. Our total is 67. So out of 67. Our probability they wore white, right, is 17. Out of our total is still 67. And that's right, the addition rule, right, we simply add these individual probabilities together. So again, I'll go to the calculator. It looks to me like same denominators. I could do 27 plus 17. Close all out of 67. Voila! Looks like about 65.7% chance. So that's pretty sweet. What's different if our event A, right, from our survey was said all are friendly versus said most are friendly? Well, this is exactly the same situation. You have to pick a response. You have to pick whether you think all are friendly, most are friendly, some are friendly, a few are friendly, none are friendly. So these events are what we call dun, 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 mutually exclusive again, right? There's no overlap there. So to calculate their individual probabilities, or the probability that A or B occurs, we simply sum together their individual probabilities. That's it. Go ahead and find those numbers in your chart and do this one on your own. So go ahead and find these in your chart, do them on your own, and then we'll check together. So what's the probability of students said all are friendly or said most are friendly? Everybody find them. Okay, how many students said all are friendly? How many students said all are friendly? Samantha? Awesome. So 783 respondents said all are friendly. How many students said most are friendly? Blake?
27,360.
Thank you. And this was out of our total 49,210. Raise your hand if you had this fraction or the sum of the two fractions. Everybody pick those numbers. That's great. That's easy. And then all we do is see what that is as a decimal. Let's not do that. Let's do that. Am I hitting the right buttons? Everybody okay? Winning. Looks like 57.2% chance. All right. So we've seen how our shoe data for shoes you wore today, right, and selecting few versus most versus all are both mutually exclusive events. Consider the following. What happens if we let event A be said all are friendly, and event B be probability randomly selected students is a girl? Are these events mutually exclusive? Well, no, because there could be this overlapping, right? This overlapping group of students that are girls and said all are friendly. And so we need to account for that in our addition rule. We'll still sum together our individual probabilities. We just need to then subtract off that overlapping portion. So here we've got our all are friendly. So all are friendly is our 783. Probability that a randomly selected student is a girl. So we'll find all the girls. We've counted the girls who said all are friendly in group A, the blue circle. We've counted the girls who said all are friendly again in group B, the girls, the green circle. So what do we need to do? We need to subtract off that overlapping portion. It's been counted twice, so we need to subtract it off once. That is, namely, girls who said all are friendly. How many was that? Let's go find it. Everybody find it. Find girls who said all are friendly. All right, how many students is that? Hans? Absolutely. So this is our overlap that we need to subtract off. It's still the addition rule. It's just the addition rule for non-mutually exclusive events. That is overlapping. So here we go. Plus, minus, and then it's still out of my total. Good job. That's it. That's the point of activity 1, right? The addition rule for mutually exclusive versus overlapping events. So if you're able to do today's examples, then you're A-OK. You're where you need to be. 783 plus 25 to 11. Uh-oh. Jacob, you got to catch that. All right. Minus 303. And all of 49, 210. Are we good? She. Awesome. Okay. So let's go ahead and have our probability vocabulary discussion as a lead-in to our activity 2, developing the multiplication rule for independent events. So not mutually exclusive events are events that have outcomes in common and can occur simultaneously. Consider the case of event 1. Or I should say number 1, event A is probability a randomly selected student from the high school is a sophomore, and event B, a randomly selected student is an advanced algebra student. Are these mutually exclusive or overlapping? Well, we saw how a student could be both a sophomore and an advanced algebra student. So this is an example of not mutually exclusive. Scenario 2. Event A is a randomly selected card from a shuffled deck is a black card. Event B, a randomly selected card from a shuffled deck is a king. Are these mutually exclusive? No, they could occur at the same time if you picked, right, a black king. So that would be which cards? King of clubs and king of spades. And so they could be overlapping. Does that mean that they are? Well, I mean, you could get a red king too, right? But we have to consider that possibility, and that'll fall into our probability. So for not mutually exclusive events, we use the addition rule. We add together their individual probabilities and subtract the overlap. And this symbol right here is the intersection symbol. We made a next slide for that note sheet. So how can we do that? Let's go ahead and do the probability. We draw a black card, right? Out of our standard deck of playing cards, 52 cards without the jokers. Half of them, right? Half of them, 26, are black. So we can write 26 52seconds. Or we could put half of the deck, 1 and 2. Or a king. How many kings are there? Well, there's 4 kings out of 52. That's 1/13th chance. And then we've counted the black kings once here with black cards. We've counted the black kings once again with the kings. So what do we need to do? We need to subtract off the black kings. And so how many are there? There's 2 out of how many cards? 52. So here's our black cards probability. Here's our king probability, and here's our black kings. Awesome. So what will we do when we get that? Well, I'm dying to know what that is too. So 1/2 plus 1/13. Jacob, you on this? Minus 2 black. I'm going to math frack it because I want to see what that is. So it looks like 7/13 chance. Let's go ahead and see what the survey says. 1/2 plus 1/13 minus 2/52, 28/50 seconds. What's that? What? 28/50 seconds? Math frack. Hey, that's 7/13. So we did it either way. Awesome. All right. So let's go ahead and make sure we're comfortable with the notation. P of A means the probability that event A occurs. P of A union B means the probability of A or B occurring. This is a union symbol, and we'll label it as such. So that's a union symbol, the same union symbol we saw back in our systems unit 7. That means or. Versus probability that A and B occur, that's an intersect symbol. That means the probability that A and B occur. Mutually exclusive means cannot occur at the same time. A student can't be a sophomore and a senior at the same time. When A and B are mutually exclusive, to calculate the probability that A or B occurs is easy. All we do is sum together the individual probabilities. When A and B are not mutually exclusive, that is when they're overlapping, calculating the probability that A or B occurs is also easy. We still sum together their individual probabilities. We just subtract off, right, that overlap. That is when A and B occur at the same time. So we subtract off that intersection. So if A and B are not mutually exclusive events, we can still calculate their probability that A or B occurs by summing together the individual probabilities. We just then subtract off that overlap, the probability that A and B occur simultaneously. Probably that a girl said none are friendly, right? That's what that last part that we subtracted off. Awesome. Questions about our activity 1 stuff then? I'm hopeful that as a result of this discussion then, everybody's up to speed, right? Anywhere you need to be as we move forward. By golly, we got the same thing. That's pretty sweet. Okay. So in just a minute, we're going to go ahead and go into our cooperative learning groups. Not yet. But first, I want to know our activity 2 goal. We're going to develop the multiplication rule for independent events. So our goal is to know when and how to use multiplication rule for independent events. Step eligible items include 1E, 3, 4B. Go ahead and put a little circle around these, please, so you know which ones you're after. 1E, 3, 4B, 5D, and 7B. And I did put these on the front right whiteboard so you could see exactly when I turn off the smartboard. A couple hints as you move forward. Number 4, please draw an area model each time. That's going to help you develop the multiplication rule properly if you use an area model. And then on the back whiteboard, everybody looks at the back whiteboard. I went ahead and posted answers for number 2, number 5B, 6D, and number 8. These are not stamped eligible items. I just put them there so that when there's just one of me and I'm talking over at this group, you could still go up and check your answers to make sure you're on the right track in between your stamped eligible items. Does that make sense? Awesome. I'm going to go ahead and stop and save the recording now.